Hello everyone, my name is Paige Tuttösí, and for those of you who missed it, I want to make a recording of my thesis defense from April 2025. I know you're listening, Adaptive Voice for HRI. So I'll start out talking a little bit about where I first was thinking when I came into my PhD. So I really want to solve some sort of problem that's currently existing in society. And something that's been a big influence on my life is that when I came to Canada from Hungary, I only spoke Hungarian. And now I hardly speak any. My sister doesn't speak any at all. And my parents put a lot of effort into making sure that we learned English so we could make friends, do well in school, incorporate into society. But it would have been great if I could have maintained my first language, but it's a lot of effort for them to try and teach me this new language and maintain the other language. And I thought a lot about if I had had some sort of companion, a robot, or a toy that could have been speaking with me, maybe I could have maintained this language. And there's been a lot of work on L2 teaching robots, but almost no work on how they should sound, how their voice should be. And given this is a speaking task, that's a pretty big gap. So the big picture, humans are going to adapt their voices based on who they're speaking to, if they're talking to babies or if they're talking to second language speakers, and they'll adapt not only the words that they choose, but also the way that they sound. So TTS is not currently adaptive to a user. It may be adapting a little bit now to the words that are in the sentence, but not to who is listening to the audio. So I identified several problems. The first one, especially working with robots, is hardware limitations. So state-of-the-art TTS tends to be autoregressive, especially ones that are zero-shot. And these will hallucinate, meaning that what you type in won't necessarily be what you hear coming out. They can be difficult to control. For example, you might be trying to have a specific speaking voice every time, and it can be changing. And they tend not to run in real time, so we say the real-time factor of 1 being 1 second to generate 1 second of audio is about real time. You also need a huge amount of data for fine-tuning. And this is really important for robotics because we don't want every robot to have the same voice. We want them to all have their own unique voices. So we need to be able to quickly and easily fine-tune. So most robots don't have onboard GPUs, and we circumvent this through the use of cloud computing, but we have often poor connectivity and privacy and security issues with this. So what we need is a TTS that's reliable, runs in real time on board a robot, is well documented, and flexible for use case specific fine-tuning. Then we look at expressive voice. So why expressive voice? In the literature, we see that expressivity can increase both affective and cognitive outcomes in the classroom. And it's been confirmed for robotic teaching agents as well. But what makes a TTS expressive? So if you're going to go online, you Google expressive TTS, you have tons of things coming up saying it's expressive TTS. But especially in robotics, what we tend to see is this joyful voice, just this happy sounding voice, higher pitch range, and it's just going to be doing this for the whole time it speaks. But are these voices really engaging or expressive if you're listening to someone talk for an extended period of time? Humans are going to change their expression over time. So what we need is a TTS where we can control this expressivity and have varied expressivity over time. Then looking at social and ambient adaptation, humans are going to naturally adapt their voice to their social and ambient context. And they'll always make an effort to be clearly heard.
But robots still don't know how to adapt their voices to their ambient context.
So with that in mind, we look at the literature, and there's been a strong focus on volume control for physical ambience adaptation. So if it's loud, turn the volume up. There's been a little bit of work also on if the voice matches how the robot looks or maybe what it's doing, but really not on the social ambience. So we need is a TTS that can adapt both to the social and ambient context simultaneously. Then kind of the magnum opus of my whole thesis is a TTS that's for second language speakers, because TTS are made for and assessed by first language speakers. And this has reduced fairness and accessibility. So if we're going to try to make some sort of L2 TTS, what we normally do is take a bunch of people speaking to second language speakers, throw their data in, turn out a TTS that sounds like L2 directed speech. But L2 directed speech tends to focus just on slowing down, and the literature shows that this doesn't always necessarily help listeners understand better. And something specifically that happens is English L2 speakers tend to struggle to differentiate English vowels. Specifically, English has long vowels and short vowels. And French and Japanese speakers, for example, will replace the short vowel ship with the long vowel sheep. So if this duration difference in the vowels is important, does it make sense to always just slow everything down? So what we need is an L2 directed TTS that improves L2 comprehension, both objectively and subjectively, that has been developed from a perception-based data-driven approach. So over the course of my thesis, I did emoji voice that's in submission right now, and it also is a demo at HRI. I read the room, which was a workshop paper at ICRA, a demo at HRI, and a full paper at IROS. Then a second language TTS, we had a bunch of things. We had What You Say, that was a poster at Journée Perception Sonore, a full paper at Interspeech. It's in submission right now for the TTS paper, and we're working on this big paper that has all of the research combined into some sort of interdisciplinary journal article. And I also wrote another paper that is out of scope of this TTS stuff that was actually a data set that we collected for distant automatic speech recognition that's in revision for computer speech and language. So I'm going to kind of breeze through these 3 papers. I'm going to do a really in-depth focus on this second language TTS. So these first 2 papers were human-robot interaction with user studies, and this last one was data-driven speech science. So for the human-robot interaction user studies, what we did is we got intuition from human-human interaction. We collected data. We made a robot implementation. And then we ran some user studies. For the data-driven speech science approach, what we did was we got some intuition from linguistics. Then we did some psychoacoustic experiments. We did some causal validation. And then we did a clarity TTS implementation. So first we're going to look at Matcha-TTS, emoji voice, read the room, L2 clarity TTS, and then talk about combining these all together. So Matcha-TTS, I talked about how this first hardware problem is that we need this like lightweight TTS, and there's a really great one available from Shivam Mehta, who is at KTH, and it was really helpful. We used it through most of our papers here. So why do we choose Matcha? It's a neural TTS trained using optimal transport conditional flow matching, which kind of solves our hallucination problem. What we type in is always going to come out. If it's a new word, it will still try to pronounce it kind of like a human. It won't just give us nonsense. It only has 20.9 million parameters compared to something like VoiceCraft that's really big. And now, since we started this, is billion parameter TTSs as well. And it's even smaller than something like Fast Speech 2, which is older and quite concatenative robotic sounding. It has a real-time factor of only 0.3 on a GPU that runs that we can find inside of robots. And it only takes 3 minutes of speech per style to create a new voice, which is really great for these robotics applications. And it has phoneme level duration control, which is going to become important when we come into the L2 speech stuff. So we'll look first at emoji voice. So a reminder of what the problem was. We need very long-term controllable expressivity in TTS. And what we looked at to solve this was emoji prompting. So what we did is we had 3 different actors, and they were reading sentences with an emoji appended onto the end and trying to express this emoji when they spoke the sentence. We looked at emojis that were both emotions as well as social signals like this cool face or a thinking face. Then we had our audio that had the text and the emoji. And this was used to fine-tune Matcha-TTS multi-speaker, and it results in these 11 different emoji voices all in one checkpoint. What we did is we then deployed this on a Miroka from Enchanted Tools and a Pepper robot. And we did some user studies. We looked at the baseline Matcha-TTS, and then we looked at only pleasant, just a smiling face, which is kind of representing what we were talking about with that joyful TTS, just one happy voice over long periods of time. And then our emoji voice that had the 11 different emojis, where a different emoji was appended onto the end of each phrase. We looked at a conversation going back and forth with a robot, where the robot was trying to help a user solve a problem with a coffee maker. And then we looked at a robot that was reading just for several minutes, a single story. What we found was indeed a singularly expressive pleasant voice seemed less expressive over this long period of speech, so when reading. And we also found that if we selected a different emoji, it helped us overcome this and it sounded more expressive for long periods of time. We found also that the perception of the voice can completely change depending on the context. So for example, in the coffee maker, where this robot's just supposed to be helping you, even though they did find the emoji voice more expressive, they really preferred this pleasant voice because that robot's like a customer service agent. It's just there to be happy and help you. You don't need it rolling eyes or being angry, things like this. And then for the same voice, but in a different task, this storytelling, it was highly preferred to have the emoji voice because it had that changing expressivity over the long period of time. So then we look at read the room. So the problem, a robot needs to adapt to its ambient and social environment. So what did we do? We observed and modeled human vocal adaptations. So what we thought about doing is going into these restaurants and seeing how people change their voices, but the problem was that we'd get all this background noise. So what we did is we collected the data on Zoom instead. People would be speaking as a waiter and a restaurant goer, and they'd have the same audio and background that were matching a certain ambiance. We looked at fine dining, cafe, lively restaurant, quiet bar, noisy bar, nightclub. And we had about 1,500 utterances at the end of the data collection. So then what we did is we clustered these using k-means clustering. We found there were these three interesting clusters. One that's the green, it's a calm, it's happening in the quieter ambiances and it has a lot lower values for most of the vocal features. Then we found the blue, which is exciting or bright. It has a high speech rate, a higher pitch range. It's happening when there's like fun music going on in the background. And then loud, which is kind of what we think of as Lombard speech, which is where you're just trying to be heard and you're making a pressed voice. So you have lower pitch range and high pitch. And this was mostly happening in the really loud ambiance nightclub. So we wanted to make minimal changes to make sure that the voice was still matching the embodiment of the robot. So we selected from the voices already existing in Pepper, where there's the neutral that matched with the calm, the joyful, which goes with the exciting and bright. And then Pepper has this didactic voice that has a lower pitch range and a lower speech rate. And we just increased the pitch on this to create this Lombard loud voice. We then had people, participants, go into a room and there was different lights, different audio and different images. And Pepper used these three different voices. The volume on the voice was never changed, only the background music volume was changing. So we were really testing if we could hear the voice, even if the volume was not changing on the robot. So what we found was that people do not like the Lombard voice in the calm ambiances. It's too high-pitched, too intense. And they don't like the neutral voice in the noisy ambiances, even though it's the same volume as the others. You just can't hear it when there's the background noise going on. We found that the joyful voice was more socially and ambiently appropriate, as well as competent and human-like in the loud ambiances, and the neutral voice was more socially and ambiently appropriate in the formal restaurant. So just by making these minimal, correct selection of the voice that goes with the ambience, we are able to improve the perception of the robot, whether it seemed like the robot was aware of its surrounding and being socially appropriate. So then we move on to our L2 Clarity TTS. So a reminder, our problem was that we needed TTS that's comprehensible by L2 speakers. And we did a focus on tense lax vowels, which I'll explain here in a moment. And what we did is we used a data-driven methodology to understand how to control perception of difficult vowels. So in English, we have these vowels that are called tense and lax, long and short. And there's minimal pairs. A minimal pair means the only thing that changes in the word is this vowel. All the surrounding consonants and surrounding sounds are exactly the same. So for example, for tense vowels, we have peel, full, and caught. And for lax vowels, we have pill, full, and cut. And I'm going to introduce this methodology that we use called reverse correlation. I'll do it using images because it's a little easier for us to visualize if we don't know what it is. So we make no hypothesis on what's going on, and all we do is we're trying to understand how in our brain we're adding up signals to generate a response. So in this case, we take an image, we overlay just completely random noise, and we have two images with this overlying noise. We ask, okay, which one of these is more, for example, trustworthy? Then we take all the ones where it was more trustworthy, and we sum up all the noise, and we get this overlaid noise, and it's the most trustworthy voice, face, dominant face, etc. We do the exact same thing with the audio, where we're doing random changes to the pitch and duration instead of, this visual noise. So what we did is we had peel and pill. We modified some automatic speech recognition to make something about halfway between an eh sound. And I heard them say pill, so that we would understand what was going on in the context leading in. We change the pitch and the stretch every 100 milliseconds, which is about 2 times per syllable. And we looked at French first language, English first language, Mandarin first language, and Japanese first language speakers, all listening to this English phrase. So as I said, what we do is we take all the ones where they answered peel, all the ones where they answered pill. I'm only going to be looking at duration here because it was what was most interesting, what we carry forward with. So at every 100 milliseconds, we sum up all the durations for where they answered peel or pill, and then we get this kernel. In the kernel, you see which language is the first language of the participants. Inside this dotted line, you see about where the vowel is falling. And if it's going up, the speech rate's slower, and if it's going down, the speech rate is faster. So what we found is we had the expected linguistic effects for duration within the vowel, being that peel should be longer and that pill should be shorter. We found this for all of the first languages, except for in English, where, English L1 in English. And here, it wasn't actually happening inside the vowel, which is maybe suggesting that when it's their first language, they're able to use this formant or the frequencies in the vowel to determine the differences in the vowel more than the duration. But then when we look at the context leading in, we see that there's a distal contrastive effect all the way across the context, or through most of the context. So that means that it should be doing the opposite of what we expect to be happening inside of the vowel. So for peel, that means it should be faster. And for pill, that means it should be slower. But interestingly, we found about 200 to 300 milliseconds before the vowel is that tipping point where it should actually start doing what we expect inside the vowel. So that means about the consonant before the vowel sound, the p in this case, we should start lengthening for peel and start shortening for pill. And this we actually found across all of the languages, even in English first language speakers. We saw it very clearly, especially in this defect just before the vowel sound. So from this, we end up with a hypothesis that there's a duration of mechanism that controls the perception of tense and lax vowels. And what we see is that lengthening a word and shortening the preceding context makes it a higher probability that the person perceiving will think that it is tense sounding, and that shortening a word and lengthening the preceding context is going to increase the probability that someone will think it's lax sounding. So we need to then validate this. So we want to know, okay, so if we have especially a non-ambiguous vowel sound now, if we're going to manually be stretching and compressing, can we actually make people answer one or the other? And we need to know how much we need to stretch and compress to do this. And we also need to know, I talked about how there was a contribution to the context and the word, how much are each of these contributing? So what we did is we added another vowel pair, full and full, and we used Matcha-TTS, where we were manually adding in a duration array. Like I said, you can control the duration of each phoneme individually to figure out how this was working. So then we'd have them listen to a sound, and they'd answer if they heard full, full, peel, pill. From this, we found that there was a bias towards lax vowels. So that means that people will tend to answer pill or full And we found it was at a ceiling. So if we make pill shorter or full shorter, it's not actually going to help. So there's no need to shorten them. But for the opposite, for the tense, we could greatly improve their performance on answering the one that we actually typed in by stretching it. So we only need about a 1.6 times stretch to have significant improvement. We also found that the addition of the context provided minimal improvement over the word only. So we decided to then move on to only stretching the word to make sure that there wasn't speech rate going all over the place. We confirmed this for French, Japanese, and Mandarin speakers, and also for English, but it has a little star because in a case where maybe the TTS is not generating very well, which seemed to be the case in the full and full, or if we added background noise or distortion, then they'd default back to this duration mechanism, just like L2 speakers. But if it's nice and clear, peel, pill, no matter how much we compress or stretch it, they're still going to hear the vowel. So we added a clarity mode to Matcha-TTS. User would normally use Matcha-TTS like this in the command line. What we added was this clarity flag, and then you put exclamation points around any word you think is difficult. You don't need to know about tense vowels. You don't need to know about lax vowels. You just need to think about, okay, if this is a second language speaker, what words might be confusing? Is it a new word maybe? Is a word have a similar sounding word? And you could just prompt a LLM to do the same thing, because underneath what it's going to do is it's going to phonemize it and look for everything that has these exclamation points, and it's going to determine if they are containing tense or lax vowels. If they do contain a tense vowel, it checks if the tense vowel has the primary stress, because they might have more than one vowel. In this case, we're good to go because pool just has one tense vowel. Then what it does is it creates this array, and you'll notice this array is the same length as each of these phonemes, and it's multiplicative. So each of these phonemes is multiplied by the matching number in the array, where across the word pool, it's a 1.6 times stretch. It ramps up into it and ramps, if it wasn't on the end, down out, so it has a nice smooth transition. And this becomes their clarity array. The way this goes into Matcha-TTS is after the text encoder, before the decoder, there's a duration predictor. This is already existing in Matcha-TTS for the speech rate, where this time for speech rate, it's the same number across the whole array. So 2 if you want it to be twice as long. And then we add a hammer product of our array, our clarity array, onto this before it goes into the decoder. So we have all this past evidence that this should be helping L2 speakers, but we wanted to be sure. So what we did is we tested these 4 TTS styles, 3 different types of baselines. So we had just based the Matcha-TTS out of box.
Bit was the first word he said, then nut followed.
Stretch, which was reflecting this L2 just slowing everything down TTS.
Reap was a more important word in the story than wooed.
Emphasis, where this is kind of what we'd imagine where if we were still speaking fairly normally, but just every word that we flag, every word that we think is difficult, we slow down both lax and tense vowels.
He wrote down but remembered it as but.
And clarity, where we're only going to be lengthening the tense vowels.
In his talk, he kept using could, but I am pretty sure he meant could.
So this is our suggested algorithm. We also added the last tense lax vowel pair, cut and caught, but we used all different combinations of consonants around these 3 vowel pairs. And we used both a single word in a sentence and 2 different words in the sentence. The 2 words could be 2 tense, 2 lax, a tense and a lax. They could be minimal pairs or not. We used all different combinations. So what did we find? We found, as we saw before, that the lax has a much lower word error rate, so in the baseline. So this means that there is, yes, a bias towards these lax vowel containing words. But we saw that we could reduce the tense error rate by almost or more than 30% by stretching the words that contain a tense vowel. But we see that if we stretch the words that contain a lax vowel, it actually does increase our word error rate and makes them start answering more often this tense containing word. But, so as expected, in the tense, we asked about intelligibility. So this is their self-rated, what they thought was the easiest to understand. They said, yes, the stretching just a tense word is the most intelligible. But for lax, they answered the same thing. They thought in their minds that the stretching these lax vowels was making it easier for them to understand, even though it was causing them to have more than 10% more errors. Then when we look at the full stretch, as we kind of were hypothesizing, if you slow it down, it seems less respectful. So it's good to be able to maintain a more natural or more first language-like speaking rate through the majority of the sentence. So when we look at two words, we see the same thing. In every case, total tense vowels, lax vowels, we have the lowest word error rate for our clarity mode. We see the highest word error rate in lax vowels by stretching them, by emphasizing these words like we would do in L2 directed speech normally, or if we tried to train this with L2 directed speech. And we see that on the baseline, these tense vowels are just too fast and it has the highest word error rate. Once again, we're seeing that this intelligibility, though, their self-rated score, they really think that they're able to use these slowed down versions of these lax vowels because they think it's the easiest to understand. But in fact, it's not. It's causing them to have many more errors. We also looked at the effort. In this case, it's the cognitive load, like how much effort you think you're putting into in order to understand. It was the lowest for stretch, actually, so it being really nice and slow had a little bit less cognitive effort, but it was also followed by emphasis. But even though it had less cognitive effort, it's seen as less respectful, but also, speaking too fast, the baseline was seen as less respectful. So then we looked at whisper. So often when we're assessing TTS for first language speakers, what we're going to do is they're going to do these MOS scores that I showed before, this intelligibility and other scores. But for the word error rate, what is used often is just automatic speech recognition, because there's been research showing that automatic speech recognition is near human performance now. So we want to say, okay, does this actually represent second language speakers? What we found is that it kind of did something. So in stretch, in fact, it had the lowest word error rate, but it wasn't behaving exactly like second or even first, second language speakers. We saw both of them were doing this duration mechanism. But interestingly, what seemed to be the biggest problem here was that normally we'd expect a word error rate to be much lower. It was actually higher here than what we'd expect from whisper. So when we saw our sentences before, we may have noticed that we tried to use sentences that were neutral semantically. So what is happening in the context won't tell us if it's more likely to be peel or pill. And without this, it seems like this is what was really tripping up whisper, in fact. So we see that slowing everything down does have a slightly better word error rate, but when we look at what type of errors are happening in these target words, we originally see on the baseline that 72% are tense lax minimal pair substitutions. So 70% of the time it's substituting something like peel for pill, but the word is correct otherwise. What we see in the stretch is we get about a 3% reduction in the overall word error rate here, but we see a big shift where now it becomes these other errors, being that no longer are we just having peel being substituted, or pill rather being substituted for peel. We're having a totally different word like parked or something. So it's actually changing the whole prediction on the word. So what we then conclude is there's a general bias towards lax vowels that can be overcome by lengthening these tense vowels. And we find that if we do indeed lengthen these lax vowels like we do if we just trained off of L2 speech, we result in having confusion with a tense vowel. We also super interestingly find that L2 speakers appear completely unaware that they're using these duration cues, and they're overconfident in their ability to use these emphasized formants or the frequencies that make up these vowel sounds. We also see that state-of-the-art automatic speech recognition is not behaving in a human way when it comes to using duration mechanisms to differentiate difficult vowels. So if we want to have accessible TTS, it's important to involve human speakers in both objective and subjective measures, especially if we're working with L2 speakers, because we see that these objective and subjective measures are not necessarily aligning. So for future work, What we want to have eventually is, all of these coming together for this teaching voice. So some problems that might come up in the future here is, if we have the expressive voice with the ambient adaptation. We have a joyful voice, it's already high pitched, and then we go into some places loud, so we're going to pitch it up more. We might run into these problems that we had with people not liking the Lombard voice, where it just becomes too high pitched. It's unbearable to listen to. Then if we're looking at something like the clarity and ambient adaptation, we actually found that when we were increasing the duration, that it tended to lower the pitch a bit. So then if we're in a loud ambience where it's making the pitch higher, is there going to be some problems with being able to understand? And lastly, and really importantly, when we have different emotions, something like anger, we might be speaking really fast. If we then are applying this 1.6 times stretch, is it still going to be too short to understand? Is there maybe some sort of minimum duration that this tense vowel containing word needs to be in order to hear this tense vowel? And so we need to consider that in the future. And I want to talk about this collaborative effort. So it took a lot of people to come together to make all this work happen. So usually in machine learning and in computing science, other people are doing some work. They've identified some problem and we're making some changes to make it better, develop newer algorithms. But I really started from this problem that I saw in society, and we had no clue how we had to solve it. We had to actually tackle how first. So we needed to know what were the components of a teaching voice. We had people from HRI in Canada, cognitive science in France, linguistics in Canada, TTS specialists helping us in Sweden, and then doing onboard implementation in a company in France. And all of this came together. And you'll notice something that we did is we became increasingly more data-driven. The first one, we kind of just assumed people could make these emoji voices, to inducing and just extracting what the humans were doing. And then we were moving from production to perception, because we focus a lot in HRI on making robots mimic humans. But maybe robots can be better than humans if we understand what the human needs rather than what the human's doing. So we moved from production of what humans are doing to modeling the perception of what humans need to hear. So a summary of the contributions. Towards building an L2 teaching voice for HRI, we looked at the need for a lightweight, controllable, and easily customizable TTS with emoji voice. We look for a TTS that's suitable and socially acceptable for a task, social environment, or ambience with emoji voice and read the room. Then we worked on a TTS that's temporally expressive over long periods of time with emoji voice. And lastly, a voice that's comprehensible for L2 speakers with our group of L2 Clarity TTS papers. And thank you all for listening. If you want to read the papers, know more about my work, you can always check out my website or check out my Google Scholar. Thanks.